Balancing redox reactions in acidic and basic conditions can be a pretty straightforward process once you get down the steps that you need to take in order to balance both the chemistry and the electrons of the chemical reaction. We're going to look at two different ways of approaching these types of problems. One is sort of the drawn out step-by-step method, and the other method actually uses oxidation numbers and your understanding of redox reactions in order to make a more streamlined process. But first we're going to do the more drawn out process, and what this looks like is you take your skeletal reaction, and the first thing that you do is just break apart your half reactions. And here you're not really identifying what your reduction reaction is or what your oxidation reaction is. Instead, you're just writing your half reactions based on the elements that you know should be paired. And so all I'm going to do is I'm going to pair this. I'm going to add the MnO2, and then I'm going to go over to the right side and I'm going to break apart the nitrogen reaction. And really, I'm not dissecting anything about the electrical properties, about the chemical properties. I am just looking at the elements that compose these molecules and ions and separating the half reactions that way. That's why I consider this to be the chemistry-free method, but very reliable nonetheless. So this is where we jump in and we begin our steps in order to balance this reaction in an acidic solution. So the first thing that we're going to do is we're going to balance the oxygens. And the way we're going to balance the oxygens is we're going to add a water for every oxygen that's missing on one of the sides. So here you see you have 4 oxygens on the left, 2 oxygens on the right. And so what I'm going to do is I'm going to add 2 waters to the right side of the equation. And next what we're going to do is we're going to balance the hydrogens by adding protons. So this is what's actually creating that acidic solution. First, we've kind of added the solvent. Now we're adding the protons. So what we did when we added the waters, we actually added 4 hydrogens. And so I'm going to add this to the left side of the equation. Looks just like this. And what we did here, and what we accomplished, is that we balanced what I would consider the chemistry of this reaction. So all of our elements are equal on both sides. But the problem is, this is a redox reaction, and one thing that's really, really important in really all of chemistry is that your charge has to balance on the left and the right. And in this process, we even made the charge balance worse by adding those H+. And so what we see on the left is that we have a +3 charge, and on the right, we're neutral. And the only thing that we can do in order to balance the charge in chemistry is we're going to add electrons here. And so in order to make this 3 equal to the 0, I need to also add 3 electrons to the left side of the equation. So now if I look at the charge, I see that I'm completely neutral on the left and completely neutral on the right. So now this half reaction is completely balanced. So let's jump over to the right and let's balance this nitrogen reaction. So first step is going to be add water. So I'm going to do +1 H2O because I'm only missing 1 oxygen on this side. Next I'm going to balance my hydrogen, so I'm going to add 2 H+ over here. And then notice what I did. In the very beginning, my reaction was actually balanced based on the charge, but I added 2 H+. And so in order to get back to being balanced, I'm going to add 2 electrons to the right side. And I can kind of double check this, and I can say, over here I'm -1, over here I am -1. And it doesn't matter that my charge is not 0. That's fine. It just needs to be equal on the left side and the right side of the equation. So at this step, we have essentially balanced our half reactions, but we can't merge the reactions until the electrons match on the left and right side of the equation. Here you see we have 3 electrons, over here you see we have 2. So we just need to make that number equal, and the way we do that is quite simply, I'm going to multiply this by 3, and over here I'm going to multiply this by 2. And what that's going to accomplish is it's going to get me 6 electrons on the left side, 6 electrons on the right side, and I'm going to be able to stack those reactions on top of each other and merge them into my balanced chemical reaction. So let's take a look at these half reactions. Once I multiply them through with this coefficient of 2, I'm going to get 6 electrons plus 8 hydrogens plus 2 MnO4 minus. And that's going to go to this manganese oxide with a 2 in front of it, plus 4 H2O. Next, I'm going to go to this other half reaction. I'm going to put it right underneath, and I'm going to put a 3 H2O. And I'm just going to keep multiplying through by this 3, being very careful to not skip over anything. And then the goal is to come up with one final balanced chemical reaction. So I'm going to actually cancel anything that's on the left side and the right side and just add these reactions straight through. The first thing that I like to deal with are these electrons, because the whole purpose of the previous step was to make sure that I can get rid of these electrons and not have them show up in that balanced chemical reaction. But then I can take everything piece by piece, and one thing that I like to notice is that those species that appear in that skeletal equation are never going to cancel out here. And so I'm going to start on the left side with those. But then I look deeper into the hydrogen ions and the water, and I see that 6 hydrogens are going to cancel on the right, but I have 8 on the left, and so those are going to end up on the left side of the equation as just those 2 H plus that remain. Now I'm going to go to the right side of the equation. I'm going to add the 2 MnO2 plus the 3 NO3 minus. And then I see that on the left side of the equation, I have 3 waters. Those are all going to cancel out, and I'm going to end up with just 1 on the right side of the equation. Now at this point we are essentially done, but I like to point out that there is one final piece that you should put together, and that is just a check. I want to check that the work that I did was correct, and I do that just based on, once again, identifying the charge balance on the left and the right. And so I'm going to see that I get a -2 here, -3, and then +2. Those are all going to add up to a -3 charge overall. Over here, I've got a 0, a -3, and a 0, and once again, those are going to add up to -3. So I give myself a big check mark for charge balance, and that is a balanced chemical reaction.